morning, ladies and gentlemen. Welcome to day 3 of Motivic Verona. I hope you had a lovely weekend. The guys at the hostel certainly have. Let's be excited for day 3 of the lecture.
Should we maybe announce that the afternoon will only consist of 1 hour?
Yes, please announce that.
Because there's a logic day.
A logic day, nice!
Yeah. There will be one lecture about reverse mathematics at 3:30. Right?
Yes, yeah.
Okay, so our usual scheduled meeting would be at 2:30 and will be. And then at 3:30 we can converge to this other logic lecture on reverse mathematics. And then after that there will be a lecture of mine, but unrelated to the so-called.
So usually in mathematics, from the axioms you deduce theorems. In reverse mathematics, given theorems, you are asking which axioms do you need in order to verify those theorems. It's exciting.
Okay. I'm a bit ill today, so it's up to you to bring fire to the lecture by doubting me and challenging me and grilling me. To that task. Okay, so let me remember, last time we stopped with homotopy co-limits and, well, derived functions more generally. And I didn't say that much about homotopy limits, I'm going to admit. And and somebody asked me right after the lecture. So let's do this a bit, because it also will lead right to the next topic, which is infinity categories. So remember how we constructed the homotopy push-out. We had, given two maps like this, compute their homotopy push-out, we factorize them. First by the mapping cylinders, something that gave us co-vibrations. And then one could go on, or we factorize these maps to C, this was a B, right? And then they give push out here, right? So this is the homotopy push out. I can write it this way, let's write an image here. And let's have a look what this actually, what is the inverse property of this thing, the strict one. So, I mean, we know what the push-out property is. For any pair of maps to some other space, from MG and MF to some Z, which coincide on this subspace A, we've got a unique map here. So let me also maybe draw these things. So what was the mapping cylinder? We had a copy of our A up here. Yeah? We took A across the unit interval and inserted with this covibration as the top thing of the cylinder. And in the bottom we identified it with its image in B. Yeah, so this P, what does P look like? Well, we have a copy of C and a copy of B, and there we have the cylinder. It's an A cross I. Now we glue these two copies of A together somewhere around the middle. That's what it looks like. So what's the inverse property then? Continuous maps out of this thing to some other space Z. Well, they are given by pairs. We can restrict this. Yeah, let's call it K, such a map. And so we got a map from this C and from this B to our Z. And a homotopy let's write it like this. And homotopy between the two maps from A that we get by going through here or through here. So what does that mean? So F is a map from...
That's a different F than the one we started with, right?
That's probably right. Let's call it F prime.
And also G prime and G.
Right. Oh, there was another G. Yeah, that's really bad. Okay. H, that was good because it's a homotopy. Then these are now called either R and S. So R is a map from, let's say, B to Z, S from C to Z, and H is a homotopy of maps from A to Z, such that H at time 0 is the thing we get by going through B. Which was called F, followed by R. Okay. It's a long expression, but maybe it's good to see this one, so it makes a bit of sense that this is so to push out really sort of collects data. Points of this homotopy, elements of this mapping set for now are really given by the datum of a map from B, a map from C, as you would expect from a push out, plus a homotopy between the two things, not just a coincidence. That's too strict, and that we saw leads to the lack of homotopy invariance in this construction. Okay, so what about homotopy limits? I didn't really say that, at least in not much detail. So, well, the trick here was factorize our occurring maps into cover brackets followed by equivalences, and we used the fact that on diagrams consisting of cofibrations, the push-out functor preserves equivalences. For limits, the dual thing is true. There's a notion of fibration. What is a fibration? Well, it's something, it's a map P. It's not that this is super important now, I just don't want to make it mysterious. So a map P from E to B is a fibration if for any square like this, the square, that means I have a homotopy of maps from A to B, and at time 0 it factors through this upper E, then I can factor the whole homotopy through the E. This other homotopic map also will be up here and will also be homotopic. The other one downstairs. And we can, in the same way as we could factorize any map to a cofibration followed by weak equivalence, we can factorize any map into a weak equivalence factor followed by a fibration. How do we do that? Well, for an arbitrary space, we can form the mapping space. What is that? These are, let's maybe do this in the pointed setting, it's a bit easier. Keep track of things then. So let's say pointed space here. So this here will be the set of maps from the interval to y such that 0 is P. So it's pointed maps where we point the unit interval by 0. And we have a map downstairs here which sends f to a relation at 1 at the end. Okay, so this space here is contractible. Why? Well, because I can shrink any path now gradually so that it doesn't really reach its original endpoint f of 1, but only stays a constant path, which always remains at p. So that's maybe an intuitive argument. You can shrink them and not walk all the way to the end. Do it with less and less. And this gives us a homotopy instant point.
This observation is one of those which are extremely easy to verify in homotopy type theory.
Yes.
Like at the same time easy and perfectly formal.
Right. Talking of type theory,
Yeah.
if you did the ACTA course, you could see this year, this collection of maps as triples R as H, map from B to Z, map from S to Z, and a witness that the two coincide on H.
Yes.
So we have been talking about witnesses of things.
Yes.
Okay, so that would be, this thing here is a vibration, that's a fact. It's just, I mean, sort of, why is this true? Well, if we have a homotopy downstairs here, we can use this extra interval space here to upstairs. So I want to go to it in order to progress a bit in this lecture. But recipe for homotopy limits is then well, special case homotopy limit of just the insertion of 2 of the base point of y twice. The strict limit would just be a point again. There's not much to look for. For a homotopy limit, we would have to replace both of these. It's actually enough to replace one of them by this path space. It's an equivalent space, so we're still talking about a point of the homotopy. And then we take the actual pullback, and what do we get? We get, well, formally we get pairs, some point here, but there's only one, plus something here. So path y to y, such that, well, this was the evaluation at 1, this map. So such that f of 1 is the base point. And f of 0 anyway was the base point in this case. This is also called the loop space. Omega. And more generally, we can factorize any map. A map like this, f from x to y. Well, what do? Yeah, maybe this was not so. Okay. We take the same path vibration that we had here now, and we take the pullback along our f. We get x cross y to the I. One can show that pullbacks of vibrations are vibrations again. Sort of this lifting here. If you pull the vibration back, then this lifting here will exist while you pull back. And so, yeah, what do we have here? I mean, this is. Can write down a section here, sending x to pair x and constant path then f of x. And I guess I'm not any longer pointed here. So this is how you, well, and this here, I mean, I told you that this thing here is contractible. So you could maybe imagine that this here comes in equivalence, because this second factor doesn't really contribute any information up to homotopy. I contract this away, and what I have is x. So this is with equivalence. Then I have this projection and this vibration. Composition is a vibration. That's how I factor these things. Okay, so why am I going into this? Of course, it's useful to be able to derive the pullback functor, but this also leads us to a point of view on what these homotopy pullbacks and pushouts are in a different way. Okay, so let's make this now. I shouldn't have wiped it away. Yes. Let's make this part 4. Affinity categories, or more accurately, affinity 1 categories. Maybe the way I introduce it now will not really tell you what's infinity about this. Okay, so our starting problem was this. We had some category and we had this class of morphisms, and we wanted to treat as weak equivalences. And we wanted to make standard constructions invariant under weak equivalences. And well, the first thing we did was actually inverting these morphisms, right? So normalization there. Okay, so to construct these derived functors, we couldn't just work in here, yeah? If you remember, we have these squares here. And we tried to fill in something here, and sometimes we had to first precompose our given functor or something. And then, in the case of homotopy colimits, from a right Hahn extension. So this, you can see that this kind of construction, it depends not only on our localized categories, it depends on the whole thing, on the localization functor. We need all of this. We need to remember C and D and these localization functors. It's not intrinsic somehow. And that's a bit sad, because somehow we would like to just decide, okay, these things are equivalents now, and then form an intrinsic object where we can just work without remembering our particular presentation C here. And you could see this pair CW as a presentation of a homotopical context. Yeah, we have our category and we have class models that we want to regard as equivalences, but there are different such pairs which present sort of the same setting, as we had this example of topological spaces and simplicial sets. And so to make something more intrinsic, it's not enough to just invert these arrows. We'll do it in a slightly more refined way now. Okay, so to motivate this, I would like to give you another universal property of this homotopy push out. We know one, it's the right Hahn extension along something. We just said that that maps out of this thing are these trizzles. R is H. What is this? This is exactly homotopy pullback somehow. It's, so what we did here to construct these homotopy limits was to put a topology on these mapping spaces, right? A compact topology. It's actually a bit of work to make this actually go through and restrict to compactly generated weak Hausdorff spaces or something. And we can do the same here. We can give a topology to this space here of maps from P to Z. So what is this? This is a... I'm still talking about the same homotopy push out. We had a map F to B and map G to C, present factorized and so on. So this is top B to C, and then pull back top. Sorry, Z. And well, we have still this H. It's not just compatible pairs which coincide on A. We have a homotopy between those. That's exactly the homotopy push-out if you construct it this way. So maybe I make that an exercise.
So is it the homotopy product or fiber product?
Fiber product.
Okay, and
Right, I should.
yes.
Yeah, sorry.
Yeah.
This was wrong the way I wrote it. And this is the
yes. Yeah.
pull back. And we can make this really an equivalence of topological spaces. And now, yeah, you can check that if you change some of these spaces here, A, B, C, by weakly equivalent ones, well, then this homotopy product will be the same, or will be equivalent again, rather. So somehow this universal property it's determined by ABC up to equivalence, and you can phrase it in this way by an equivalence to another space, the maps out of it.
And again, in homotopy type theory, it's trivial to prove that. And you do not need to know anything about the compact open topology or compactly generated Hausdorff spaces. Yeah.
But I mean, here you also don't. You just need to know that this has the exponential property.
Yes. Yeah.
You know, you need to know that there is a space such that top state was B to C. It's homomorphic, and it's not even necessary in our case. Put this here. So
Yes.
you should, for this exercise, just use that there are such exponential objects in spaces.
Yeah.
I mean, it's not trivial that you can set up a category top where this actually works, but it's possible. So somehow this, I'm just putting this here as motivating remarks, so what comes next. So you could say that the universal property of this homotopy push-out could also be phrased in terms of some homotopy pullback. I mean, that's a bit really circular, but not in what comes next. So mapping out of the homotopy push-out turns this into a homotopy pullback. That's now for spaces just what I'm talking here, although it should work more generally. And so our strategy now to define something more intrinsically, which does not need to remember this original category C for localizing, is the following. So in category theory, you define limits, let's say, and co-limits, just by the mapping properties, of course. I mean, let's say, again, push out in any category. Of course, here's the defining property. For any pairs of maps such that the position of these maps to A makes them coincide, there's a unique such map. So we can rephrase this as saying C PZ is isomorphic to the pullback C BZ cross C PZ over the two things that I get when I precompose the nest from A. So is it clear to you what I mean by this thing? Oh, yes.
Yes.
Okay. So to define push-outs, for example, in this case, in any arbitrary category, it's enough to know what pullbacks and sets are. And the same with this is enough to define push-outs in any category C. And likewise with pullbacks, of course are defined by a property of mapping into them, so I would put the Z on the left-hand side, and I would still say that, okay, Newton's property of a pullback is given by the isomorphism of sets into some other pullback here, of sets now. So if we know what a pullback and set is, now computed, then we can define and possibly check in particular cases what is a push-out or pullback. And that's the strategy one can adopt for making this more intrinsic, these derived functions. So we know what homotopy limits and spaces are now. Topological spaces or simplistic sets would be the same kind of setting. Now we can say in these terms what it is for any relative category of any such localization situation. So it's time to start numbering something here. Let's define the Hammock localization. This was invented by Boyer and Kahn, and is a refined way of inverting arrows in a category. And the outcome is not another category with a universal property inside the world of categories, but it's a category enriched in simplicial sets, also to say in homotopy types. So, what do I do if I'm given a relative category C with a class homomorphism W? To it, I associate the category enriched in simplicial sets name, LH, WC. We have to say what the objects are. It's the same as we did before with our usual localization. And now we have to give a simplicial set of maps between any two objects. And so
an ordinary category has Hom sets, and a abelian category has Hom abelian groups, and a category enriched in simplicial sets has Hom simplicial sets. Very easy.
Yeah. So I have to say, if you remember what a simplicial set was, it was a diagram like this: 0 set, think of as one simplicity, as points, zero simplices. First sense we think of as intervals, one simplices, and we have a start and an end, beginning and end. Then we have two simplices which are triangles and have three sides which are intervals, so we have these three left and so on. So I have to say what is the nth set here and how to map downwards and also upwards. These other directions. And here's how. So the nth set in this simplicial set is the set of hammocks which start at A. Of width n. So the start here is called 1, 2, 1, n1. And then, if you remember our construction of the localization before, we had these zigzags. We do the same here. We have we allow wrong way arrows, but only if they are W.
Mm-hmm.
And well, we end somewhere that any K.
Mm-hmm.
And the end ends B. And we have vertical maps always going downwards and always consisting of arrows in W. Maybe here, B1, always downwards. And so that's what a hammock looked like. Hammock means amaca in Italian, I looked it up.
The first arrows are in W.
Whenever, I wrote down a bunch of conditions now. So whenever an arrow goes wrong way, it should be in W, as we had it for the usual localization.
So the very first ones also should be.
Obviously, because they go wrong way, they must be in W. If they go the right way, but it's not a condition. They could go the other way and then be arbitrary.
Ah, okay. Okay. And they could be mixed, right? Like the very top one goes backwards.
No. The next condition is in every column they must go in the same direction.
Okay.
This diagram should commute, so I better start writing down these things.
So the K, there are two Ks here, or?
There shouldn't be.
I think there's only one.
K, that's the length of the hammock.
Yeah, and what is the letter below?
N.
That's an N. It's also here defining the N simple set, and that's the width of the hammock.
Mm-hmm.
And the K is, where is it on the left on the notation?
It's not, because K may
So
range.
here we go.
K is right.
We allow hammocks of any length.
Yeah, okay.
This whole diagram should be commutative.
Well, die vertical morphisms.
So that's the N. It has to be N. It has to have N rows. Actually, sorry, it has to have started at 0. Otherwise, it would get something set. That was a flaw. Yes.
So you just forgot the one between x 1, 3, and 2, 3.
Oh well, I just stopped drawing it. Claim that I didn't forget it. Okay. You get the image of how this thing should look like. This diagram should be commutative. Vertical arrows should be in W. Then wrong way arrows should be in W. Wrong way in the sense that I want to go from A to B, and sometimes I will travel backwards. Yes.
Mm-hmm.
Yeah, lengths are arbitrary.
And can each horizontal arrow decide whether it should go in the right or wrong direction?
How would an arrow decide something?
No, like, I mean, are all diagrams of that shape allowed?
Yes.
Yeah.
I mean,
So especially like in the in the zeros column, that was that earlier question. Yeah. So they can either all go to the left or all go to the right. Right?
Yes.
Okay. Good.
so in every column, I could have like maybe written a whole column of A's and identities here. That would be easier, but then it would look like a hammock.
Yes. Right. Yeah. Yeah. That's very important.
In every column, all horizontal arrows point in the same direction.
Okay.
So that's the set we start with for the level n, and we still identify some of these. Oh god. Namely, for example, if we have an extra column of just identities here, we identify it with a hammock of length 1 shorter.
Okay.
That's the place. Relation generated by pretty much what we said before about the zigzags when we constructed the localization, except one thing that we can cancel a wrong way arrow and a right way arrow if they are the same. By so. So, if I have a column only consisting of identities, I can just identify that hammock with a hammock of length 1 less. Or I can just fill it in more. And I can compose. Composing, so if I have two columns where the arrows show the same direction, then I can compose those two. Again, I have a hammock of 1 short. Composing, let's say, columns. Pointing in the same direction. So that's 2 of the 3 conditions we had for the localization. The third one was that we could cancel, if we had an f pointing in this direction and an f pointing in this direction from W, then we could cancel them out. This we don't say.
Okay. Because now instead we have higher simplices.
Exactly.
Okay.
Is the construction okay? I mean, it's of course it's a monstrosity in general. You don't know how to deal with this, but it's just a category in which it's a visual sets. I can yes.
Oh, why is it a set?
Was it a set? Well, the same problem applies. It's not a set.
So it's not a simplicial set.
Yeah, no,
Right. It's a simple class.
no worries.
But right. Yeah, same problem applies as before. Of course, it's worse because before we could cancel more. We had a better chance of the quotient being a
Right.
set. Now that really detonator as a theoretical universe. But let's not care.
Can you prove the composition of morphisms? Just kidding.
Well, composition, you're right. I mean, we're not done yet. Actually. So we have to do a bunch of things, right? We just defined the sets. Now we have to define the structure maps of the sets. We have these phase maps. So given such a hammock here, I have to produce in n plus 1 different ways a hammock of width 1 less.
Yes.
And what do? I just compose 2 adjacent
Rows.
well, columns.
Oh.
I mean, I compose 2 adjacent vertical sets of
Rows.
Rows, yeah.
rows. Right? Yeah.
So it just said north in the vertical direction.
Yes.
Sort of.
Yeah.
Except you divide out something and it's not a node. It would be nice to just say that, but it's not.
Yeah. Okay.
Okay, so face maps given by composing vertical arrows, thereby forgetting one of these rows, then it's gone, right? But I mean, so if you know what the norm of category is, you're right. It's for the reason that the norms of categories are sets that you already can prove immediately that all the relations are satisfied. And we have the degeneracy maps. So that goes the other way around. Given a hammock of width n, we have to produce a hammock of width n plus 1, where we just repeat one row and throw in identities everywhere. We get vertical identity arrows. To be able to do that, we should better demand that identities are part of W.
Yeah.
Well, that's harmless, of course. It's important vertex. Okay, we want a category, rich and sets, so we still need to say how to compose two such morphisms of level n. Well, we just glue these hammocks together. I mean, they go through some b in the middle and then go. We can just like unstretch this b with a lot of identities vertically.
Yeah.
We achieve the same shape. Okay, so that's a horrendous construction. Given a category and a class of equivalences, which probably has to satisfy. So it should also be closed under composition, so we can probably. I mean, in practice it always satisfies 2 of 3. We can produce a sufficient category this way. Doesn't look like we've gained much, we have produced a horrible thing, but now we can define more intrinsically what homotopy limits and colimits are. Okay, I wipe this out now. I would protest. That comes further questions. Okay, now we can define homotopy limits and colimits more intrinsically. And now we have a category. A hammock localization of C at W. And the whole column of a diagram here, something that should now satisfy this universal property with respect to these homosimplicial sets. So let's do it by example. So we have this here, a diagram in C, and we want to compute the derived push out. And just say, okay, it's the following. It's square. It's not right on the square. So it maps out of P into any Z. Now that's a simplicial set. And if I really want to talk about spaces again, because you're more comfortable with that, then you can put the geometric realization bars around it. Then you really have a space. And we can demand that this is the homotopy pullback of, B that over AZ with EZ. This is the expression. In simple sets, or equivalently, topological space, if you just realize everything geometrically. And now this is sort of an intrinsic object. Yeah, we have this little category. We can just talk about push-outs and pullbacks, homotopy push-outs, homotopy pullbacks in this thing, where everything is only now required up to equivalence, weak equivalence. In simple sets.
And canonical weak equivalence, right?
Yes, right.
Yeah.
That's canonical map to here.
Yeah. Yeah.
Push outs. Yeah, pullback. Okay, now you have all the while. Let me check the time actually. I mean, it would be a totally legitimate question now, so is this really necessary? I mean, this seems to be a monstrous object. And yeah, where are the advantages? Yes. That's sort of, it's an intrinsic object up to equivalence of infinity categories, which I will define next. So it's something where you do not any longer have to distinguish these presentations. Yeah, we had these pairs of different categories like topological spaces and equivalences and simplicial sets and equivalences, which sort of present the same kind of setting, and they will give rise to equivalent infinity categories or simplicially enriched categories like this. So let me define this next. Where am I with my numbering? Probably not very far. So if I have simplicity enriched categories, and I have an enriched functor, what does that mean? It means I send objects to objects, and I have maps of simplicial sets, commuting with all the structure maps, faces and degeneracy maps. Yeah, I have this index running through the levels of the simplicial set. This I call an equivalence, also called Weyler-Kahn equivalence. this will be continued in a bit. I first have to define what's an equivalence in a simplification category. So this is 1.5. And it's not a definition, it's a proposition. Do you have a question back there?
I don't understand what you think
Here? Yeah, I was about to define what is an equivalence between simplicity enriched categories. And this bit came from a previous layer. Yeah, let me come back to this. I'm not writing it here, but there's written here, I have an enriched functor, that means I map simplified sets between every two objects, maps of simplified sets. The Dwyer-Kahn equivalence, this is another name of the inventors.
So, what was the Dwyer-Kahn equivalence?
No, it's not.
I'm about to
Define.
do two other things before I can define it.
It is about to define.
Yes.
Yes. So,
Building up some suspense.
yes.
It's open.
Yes.
And I think let's start with the definition. I'm sorry for the back and forth here. So, given a simplicity enriched category, it can define its homotopy category.
Mm-hmm.
Whereas the category with objects the same again. And morphisms. So what do we have here? I want to define an actual category now. This has to be a set. So I will just take pi 0 of this simplicial set that I had. And this category, I have a simplicial set of morphisms from A to B. And if I didn't really define pi 0, but it's really a set of connected components in the sense that I can connect things by one simplices, so by path with one simplices.
Without caring about the direction.
Without caring about the direction, exactly. But it's just the same as, I can take the topological geometric realization of this simplicial set. That would be the same.
Mm-hmm.
So that's the homotopy category, and then I have following fact that the homotopy category of the Hammer localization of some category, W plus morphisms W, is the localization in the usual sense. Proof? Well, in our definition of the Hammer localization, we had two of the three relation generators that we had for the actual localization here, the categorical localization. And now we just have to see that the third one also comes about. And the third one is exactly given by these connected components. And so here's proof by picture. So what is missing? If we have two arrows occurring twice, but one time is going in the other direction. Let's not put names to these things. Maybe let's do x by x, b, and then just do it for a hammock of length 2, width 2. That's because That's all we need to get to connected components. We just need to look at paths. Well, here is a path from this thing to the thing where I've cancelled away the f's and put identities instead of them.
Yeah.
So this is the one syntax between that zigzag and that. So they lie in the same connected component, and I have then also the third relation that's missing from my actual localization. Let's call that approved.
Sorry, could you say more about this proof?
So I was defining a category by giving you, well, a set of morphisms between two objects.
Yeah.
This set, I said, should be the set of connected components of my simplicial set.
Yes.
That's the same as path connected components in the sense that a path is a zigzag of one species. And here, so from the beginning in my hammered localization, I had these two relations imposed that I can delete identity columns in the horizontal and compose things. That's what we have in our actual localization, right? And here we also had what actually made this thing to the localization, that we can regard the wrong way f's as inverses of the right way f's. That's the canceling. And up to connected components, up to this relation of lying the same connected component of the simplicial set, such a pair of wrong way and right way f's is a zigzag where these are identities. And composition was, yeah, I mean, concatenation. Then
When does this conclude? Okay, this one simplex between I see a.
So this and this become the same representatives of the same morphism in the homotopy category.
I see, and that's the same as CW minus 1. Yeah.
Yes.
Yeah.
I mean, it's sketchy and exercise completed if whatever you feel is missing. And now comes the thing that was lacking. 1/7/8.
It's good that the rationals are dense in the reals.
Absolutely. So two objects in a simplicity enriched category are equivalent if they become isomorphic in this category. That's what it is. Okay, now we can come back to this definition of when an enriched functor between simplicity enriched categories is an equivalence. And this is meant to capture what it means to really represent the same optical contexts. So an enriched functor, what is this? This is a map from objects of C to objects of D, and collection of maps of simplicial sets for each pair of objects, from C, A, B to D, F of A, F of B. And this is said to be a required argument if you should now write this. You couldn't read it. Boyer and Kato were the pioneers of this kind of infinity category theory. If first every object in D is equivalent to one in the image, and second, all of these maps are weak equivalents. Yeah, the first one says it's essentially surjective, the second says it's fully faithful in our new world case. So if you still prefer homogeneous spaces, then put the realizations there, that's by definition the same requirement. This means that it's objective. It means maybe quotation marks because it's not exactly, but it's sensible replacement in our new context. Okay, how are you holding up? I mean, last time people suggested that we could have a break in the middle of these 2-hour sessions. Maybe that's also time. Then let's take a breath.
Yeah.
Okay, then let's go on. Now we know what. Well, actually, I didn't say what an infinity one category is. It's a simplicity enriched category. Up to equivalence. So it's. Here's the point. We want to see simplicity enriched categories as infinity categories. So what is the intuition about infinity categories? You know categories. They have one object and morphisms between these objects. Two categories. I mean, you all know one category. That's the category of categories. It has objects categories. Morphisms are functors, and there's two morphisms between the one morphisms. That's natural transformations. Right? So infinity categories would mean that you have morphisms of higher level for all levels. And the standard example that you should think of are topological spaces. If you have a space, then you can take the objects as the points as objects, the paths as morphisms, the homotopies between paths as two morphisms, and so on. You have homotopies between homotopies, and this never stops, of course. So that's one thing you can think of as an infinity category. So here in our simplicity enriched categories, we want to think of these as infinity categories. Also, well, we have objects, of course, by definition, and between any two objects, we have a simplicial set of morphisms. That means we have the vertices of that simplicial set. Those are the one morphisms. We have the edges. Those are the two morphisms, and then we have higher simplices. So those should be some of the higher morphisms. So there's many different models for infinity one categories, since we just defined these Dwyer-Kahn equivalences, right? So we have the category of simplicity enriched categories and enriched functors. And we have the Dwyer-Kahn equivalences. And that's a relative category again. And we could have completely different models, and actually there are different models, to say what such an infinity one category is. And they again give rise to the same homotopical setups if you start to try to compare it. So there are different, to say, models for this, and that's where the term model category comes from, if you've heard that. So this is one of many models for infinity categories. And the one most developed and the most in use nowadays is a different one. There you encode your infinity category as a simplicial set, not as a category in original simplicial sets, but just as a single simplicial set. I can tell you about this in the other sessions if you want. And that's the thing that has just the best developed theory nowadays by Lurie. It was started by Joyal, or initially defined by Gordon and Vogt. But yeah, Lurie is the one who wrote huge volumes of theory, and it's really ready to apply nowadays. And if you really come to a situation where you need to use infinity categories, then that's probably the one to go for. So I could not pass a lecture on this without notice. Okay, so there's another nice fact that I want to tell you. And that's Dwyer-Kahn, I think. So you could think that, well, we wanted to invert some errors in a category because we came from usual mathematics and we find some objects and they form the category that we came up with a natural approach of equivalence. And of course, okay, now I showed you how to produce a simplicity enriched category from such a thing. But isn't this a crazily big setting now? Why do we have to really develop a theory of simplicity enriched categories or infinity one categories in some other way? Well, we didn't go very crazy here. Every simplicity enriched category is actually equivalent, Dwyer-Kahn equivalent, to one coming as a localization by a usual category. So we didn't do anything beyond what we actually want. Every simplicity enriched category is Dwyer-Kahn equivalent, in the sense we said now, to the localization of some other category G by some class of modules.
Do we need some kind of presentability or?
No, not for this. This is completely general infinity category theory.
Yeah.
Has a nicer form, even this theorem by Barwick-Kahn. They look at relative categories, so just really one category with a class of morphisms, and they show that there's a model structure of this which is equivalent to, for example, this one of the quasi categories. So it's really this highlights that we are not going crazy here or like doing something overly general. That's exactly what we want. We want to localize morphisms in usual categories.
Which authors are doing this? Could you repeat the names?
Barwick comes. Mark Barwick and then Kahn. I'm not sure, what exactly they give it. They give it to Hebel categories which themselves are equivalent to quasi-categories, also usually enriched categories. It's yet another model, but if you know that these are equivalent, then they have another article where they show directly that the equivalents in their model structure on here are the Dwyer-Kahn equivalences of the pre-image described one equivalences. But this here, involves model structures which we don't talk about.
And given a simplicity enriched category C, how hard is it to describe that category D?
Probably impossible in general. I don't know.
So there's no simple construction which I can do with the C in order to obtain D.
Ah, wait a moment. That's not true. I
Yeah.
can just, I guess, take
Yeah. It won't be
the
the
zero level of my superficial sets
Okay,
as
yeah.
a category, and then
Okay.
localize that one by the
Okay. By whatever is getting inverted in the
homotopy category.
Yes.
Yes. Actually, that sounds like a reasonable case.
Yeah. Okay.
That can be made an exercise. Check whether this works. Category construction. So, given a simplicity enriched category C. Then get a usual category, call it C tilde, and objects are the same. And C tilde B should be CAB and then the zeroth special set. Then I would define the equivalence for which I localize as the pre-image of the isos. Yeah, I get a functor from C tilde to OC. And whatever goes to an isomorphism there, I declare it. It sounds like a reasonable guess that this gives us back the same simplification category. Or same up to where hard equivalence. Okay, so I have to say something motivic eventually. So let me wrap up this section here of infinity categories. I just gave you an idea. And this now I take as an excuse, so to just gloss over this kind of derived functor business and to replace spaces by other spaces. I just say, okay, everything's derived from now on. I just work in this infinity category, and that's where I use my usual language. So in infinity categories, we now say co-limit, limit, and so on, Kahn extension, and whatnot. For what would usually be the derived such functors. And for what has the universal property of the usual concept, but now up to equivalence of the mapping spaces, the homosimplicial sets. doing it, but here's an example. We just will say, now if I have a special enriched category and an object in there, I will just write sigma x for the pullback now in this new sense of no, push out, sorry. Of x along 2 points. Why is that? Because that's what we get in spaces if we just derive this stuff, right? I mean, so we would have to replace the mapping point by the mapping cylinder, and that would be our x. And at the bottom, we collapse everything to its image in the point. Same here, like this, and then I glue it, and then I get a suspension of x. And this now I just say, okay, yeah, this is the suspension. That's the kind of spirit I will do in these lectures for working with, and everybody does really, for working with infinity cables. Just maybe to make another remark, so what does this mean? This point, it's a terminal object in well, let's say the infinity category spaces or any. And that means that the space of maps from any object to that one is contractible. That's maybe another. So maybe easier instance. So let's call it X maybe rather. X is a terminal object. Not if it's really terminal in my specially enriched category, but it's terminal to equivalence. So that means if C from Z to S is totally equivalent to a 1-point space for all of Z. That's, if this really was an isomorphism, then it would be an actual terminal object. Now I mark things up to equivalence. So that's the spirit here. Okay, so then the time has come to remind you of this hexagon. Go one step further, because we all were stuck in the first step of this hexagon. So in the first lecture, I started with this picture, right? Maybe that's now this whole section already. So for those who came just now, I recalled what is a cohomology theory by the axioms, and I told, well, what is it? It's a certain kind of functor of convertible spaces to sequences of abelian groups. Variant. And actually, so last time I said, okay, for example, a cohomology theory is something that sends weak equivalences to isomorphisms, so we can pass here through the localization. So now let's go infinity categorical and write some some more refined localization here.
And the category top at the top,
Yes.
this should then also be a simplistically enriched category, right? So that
No, this is for now just really the actual. I mean, every
But then-
category is a simply enriched category by taking
discrete.
discrete
Okay.
sets. So there's only 0 level, and then the higher levels all the simplicity are degenerate.
Yeah. I mean, we need that in order for the arrow to make sense, right?
That's right.
Yeah.
Okay.
Okay, and it's kind of surprising that to me that we turn top into a simplicial category by ignoring the topology we could put on the home sets, like compact open or whatever. And
Well,
just
if you do that, then we're here. That's actually what you get.
Nice, okay. Okay.
And that's what is commonly called spaces, and it is what, as I mentioned, plays the role of sets in this infinite category theory. For example, you can define colimits and limits by colimits and limits in sets in usual category theory, and here we do it in spaces.
And with the curly C, you mean top.
Oh, thank you.
Yeah.
And these W is a big equivalence.
Yeah. Yeah. Okay.
So then we had pointed spaces. That's a harmless enough function here. It's just really, it's a common category. Spaces receiving a map from an object, meaning all the maps which are base points. And I'll just say, okay, equivalences are still those here, so I could also first form top star and then localize at those equivalences. You can also just take the common category in this simplicity enriched sense. Not worth thinking too much about it. And then the next thing we had was the stabilization, coming from the fact that cohomology theories have this suspension isomorphism. Yeah? So we have this thing here, H star of write an Hn, sigma x is isomorphic, naturally isomorphic, Hn minus 1 of x. So the suspension map, which is something that we have in any unit category, by the way, where these pushouts exist, they don't have, is something that causes, upon applying cohomology, just a shift here. And shifting is an invertible function. I can just shift back. So this should factorize through something where the suspension becomes an equivalence.
Yeah.
And that's the next topic now. That's stabilization. So there is a universal functor which makes a given angle functor here, which is suspension, into an autoequivalence. That's the thing we can factor through if it exists. And I'll show you how to construct it. Well, since we have this half hexagon here, next thing was what is of the algebraic spectrum, which is derived from the intermediate groups, and then take a cohomology of the complexes that make up this thing. Okay, so that's the next section. It's about stabilization, which is this process here. And
So what are the functors of spaces sigma inverse to HC mod? So this I suppose is spectrum, right?
this is spectrum.
Is this like tensor with HC or something?
Here, yes. All right.
And the map, the functor after that?
This here is the cohomology. I mean, if I have a chain complex, that's what for every object here I can write chain complex as a representative and take the cohomology.
And the top to ABC is
Like sequences of the leading groups.
so what is the functor? Cohomology.
This one, cohomology.
From top left. Also it's also
Oh, this is singular cohomology.
okay.
Let's go to Z.
Yeah.
Okay.
so it's not so clear why we actually want to do this thing here. It will become clear when we start working there. As a rough guide, I can tell you that yeah, I mean, these places are more and more workable along the way. This year, I mean, it's now an infinity category, but it has a homotopy category, and that homotopy category is additive. We have a billion groups as home sets. So as we go through these places here, we get more additive and more algebraic, and it's good to have these gradual degrees here. And well, as I said, things are representable here, cohomology theories become representable here, and that's a real bonus. We will see. Okay, so what do we want? We want, maybe put it more generally, given a category, an infinity category now, and an end functor, we want an initial functor where this end functor becomes equivalence. So what would that mean? That's what I denote by f to the minus 1. We have a continuation of this f bar, which now is an equivalence, such that for any other d and end functor, every other functor h, which commutes with these end functors, wrong. Oh. There should exist a unique functor theory. And all the time now, I'm here in infinity categories, otherwise it would be hard to construct this. It actually was a major obstacle in topology for a long time to think reasonably about this. So what I want here, so I want the initial one among functors which respect this automorphism or this endomorphism, right? So first applying suspension in our case, and then going here should be the same as first going here and then applying whatever is here. For example, the shift functor. But being the same, that means up to equivalence. Yeah? Now we are always doing everything up to equivalence, but it's actually a good strategy to not think about this too much. And this uniqueness is also up to equivalence. There should be a contractible space of functors filling this thing.
What do you mean by equivalence of f bar to f bar?
Here, this should be an auto-equivalence now. Ah, yeah, this too, sorry. This is part of the... So, okay, I can form a category of whose objects are infinity categories and endo functors. Let's say a functor between two such things is a functor from C to D. Plus an equivalence, I copy it, H after F to G after H. Okay, it's can form an infinity category of infinity categories with endo functors. Objects are pairs, infinity category endo functor, and morphisms are this. And in this category, we want an initial one where this endo functor becomes equivalence.
And equivalence means via Khan.
Via Khan.
Yeah.
Always via Khan.
Yeah.
so how do we do this? Well, we can take the case of modules. If you have a module or a ring, and we have some element, let's call it R, and we can localize the module at this element, the ring, right? And here's one way of constructing it. You can construct it as a co-limit of just repeat multiplication with R. So why is this the localization? Maybe we should check that it has a Verona's property. Right. So the localization should be a map from our original module to this one, which is initial among those where modules where R receiving a map from M and where R acts invertibly. And so such for all homomorphisms such that here multiplication with R is invertible. Well, how do I do this then? I then need to map from here, right? And I just, well, I take my M here. So what's the map from M to its localization? It's just insertion in this first part here. And for this to commute, I just have to apply H again. Now, if I go from M here and want this to still commute, then I have to apply R to the minus 1 H. Which I can because here there's an inverse to this. And so on. This defines a map here. And we maybe also should check that this actually that R acts invertibly on this one here. So why is this true? Confusing.
Given an element in one of those M's.
Yes.
So
yeah, let's remember how to construct this co-limit. Modules is just
yeah.
Maybe we should give the numbers, but it's all the same M.
Yeah.
And then we identify things with their image here. So we have an M coming from the nth level, then yes.
Yeah, then I think the 1 over R times Mn is given by the same Mn, but now pictured as an element in the next capital M.
Right. Because that is what we get by multiplying with R.
Right.
This thing.
Yeah.
Seen as living in the next level.
Yeah.
Well, exercise, check that again. It's really interesting. It really is a construction of the localization of a module. Okay, now how can we construct this stabilization by a functor with exactly the same strategy? We just take our given category C and form this co-limit of C and apply this formula. The co-limit, of course, means in our infinity category of infinity categories.
Mm-hmm.
So yeah, now it seems of course impossible to determine what we got by this. We just know it exists. But for the same reason as here, it will have this.
Mm-hmm. And what works wrong if we work in the setting of one categories?
A good question, I don't know. Maybe nothing.
Yeah.
You can check it.
Yeah. Okay. I mean, just because you earlier you mentioned that it was a great breakthrough to have that in the infinity, or that we needed that breakthrough of infinity categories in order to properly have that localization.
That is true. And I was thinking of really understanding the category of spectra in the case of topological spaces.
Uh-huh.
But actually, I mean, just as a construction, I don't see an obstacle to this existing. But just the outcome might be maybe not that useful. But let's.
Yeah.
So let's find an example in the usual one categories and try to form localization like this.
Mm-hmm.
But I think these co-limits of categories, of course, are in general hard to compute. You have to collect copies of the same category all along, like here, and then you will have arrows from every copy of your category, and then you have to allow which can come from many levels here. So it's a messy thing.
Yeah.
I mean, of course, this might go totally wrong. I have no idea. Okay, but let's look at the case of topological spaces. 10 minutes ago, maybe. Something we can still do. And see what we get in the case of spectra. And for converting the suspension and the functor.
Are you sure this definition works just like you stated it? Just usually you want some locally presentable stuff, blah blah.
Absolutely, that's what I will do now.
Okay.
But I mean, this exists.
Oh, okay.
It's just not really usable very well. But this was exactly what I was going to say next. I mean, we can do this with a plain infinity category, but we can also do it within some other infinity category of infinity categories. Maybe, and we will do it in presentable monoidal infinity categories actually later on. So yeah, I mean, not clear how to do this. So when I was checking out the example of spaces and the suspension end functor, I want to invert this one. So spaces are not just any category, it's a very good category. They are spaces is complete and co-complete. It's an infinity topos even, but we won't say what that is. Spaces star, okay, spaces star is no longer an infinity topos. And it is what is called presentable. That means, additionally to being complete and co-complete, we also have a set of objects, not a class, set of objects, such that every other object is obtained by a filtered colimit of these. So that means every space, so let's call it a director here. Of spheres and the one-point space. So that's exactly the statement that every topological space is equivalent to a CW complex, weakly equivalent. And CW complexes are what I can glue together by using spheres and disks. And disks are points now, because they're equivalent to a point, effectively. And so we are actually, when we do this here, in a better world than just any infinity category. And you want this, look at this stabilization to happen within the world of presentable categories. So that's where we do this. And here's one thing that's useful about it. It's called, so there's a natural notion of functor between presentable categories. So there's something like a joint functor theorem for infinity categories. So if you have let's say, colimit preserving functor between presentable categories, then it always has a right adjoint. It's called and functors which are left adjoints, meaning colimit preserving. If you know the corresponding thing in one category theory, there's something like this too. Presentable, locally presentable categories, that's what I call them. And as in usual category theory, if you have a functor and it has an adjoint, then this adjoint is uniquely determined by the functor. Uniquely determined now means up to equivalence, of course, but let's stop saying that. So we also have this category of infinity categories and right adjoints. Mm-hmm. And that's just the opposite category of this one, because the arrows go the other way, but they completely determine this and this completely determines that.
And the right adjoints are precisely the limit preserving functors?
No, I guess you need the filtered colimit preserving.
Okay. Yeah, good.
Pretty much. It's always a good guess that usual theorems from category theory just go through. Mm-hmm. Of course, you have to check, and the proofs can be horrible, but it's surprisingly consistent with this. Mm-hmm. So, if you want to read more about infinity categories, one great place to read about this, if you can read French, is Jasinski's Bourbaki article on this. And he starts it by saying, yeah, infinity categories are new semantics for the language of category theory. You just speak the same language and now it means something else. And of course, it's not always true. I mean, it always has a true now, these same old statements. The question is whether the old true statements are still true now. But very often this is the case.
Do you know often an example where it's not the case?
Yes. So there's a notion of infinity topos, and classically every infinity topos is a localization by a Grothendieck topology of some pre-sheaf category, and here no, this is a hypercompletion process to get all the infinity topos.
Okay.
But it's a rare thing, I would say, in average. Okay, so we have this category of presentable infinity categories and left adjoints, and that's where we want to take our inversion, because then we stay in the same nice world here. And the outcome will be a nice, presentable, complete co-complete. That's automatic, that's included in this presentable category. That's what we want to get. So, let's look. Let's take a look at this functor that we want to invert. That's the suspension functor. Look at it as a thing in top star or spacer star. And let's look at it in top star, because still everybody is more comfortable with this. So, from the get-go, we should have chosen our topological spaces such that we have this junction property. We already introduced loop spaces and everything. So what is this? What are the maps here? These are homotopies of two functions from x to y. These are maps from here to the path space. That's just a junction thing. You can look at a certain subset here, namely maps from the suspension x to y. Why is that a subset? Because, or subspace. Well, because this is a quotient of x cross y. We switch together the top and the bottom, and so these are all the maps from x cross I to y, which identify the top and the bottom as base point.
Yeah.
And this bijection restricts to something on the other side here, which is, well, now here I'm looking at the path which starts and end at the base point also. Maybe a good exercise. We don't know it already. We have this adjunction, and this passes through to spaces. I'm sort of writing this. That's confusing. So now we see this in the infinity category, we have the junction like this. Okay. So what about our stabilization now? By construction, what we stabilize is the suspension functor. And that would be this thing here. This star. And we just take this co-limit, linear co-limit, of a diagram where each place we apply is suspension. And this we want to do in presentable categories with left adjoints. Okay, but left presentable categories and left adjoints are the opposite category of presentable categories and right adjoints. And we can just take the limit in there. Co-limit in the category is the same as the co-limit in the opposite category. Yet another standard effect which goes through. And now I have to put at every place here the adjoint. That's how the equivalence goes between press L and press R. And the adjoint is omega. And that is actually now a description that is useful. I know I'm slightly over time here, but just say a final thing.
Yeah, don't worry. It's okay.
So your colimit in this TRL, is it the same as you defined in the first place? I mean, your very first thing was take an arbitrary category and do this colimit in category.
Yes.
Now you take in another colimit. Is it the same?
No, it will be a different thing.
And it will be better.
So
It will be better. If I take the stabilization
definition was
in
just motivation, and now
Yes.
forget this. Right. Perfect.
We have certain,
No sarcastic.
No. Yeah, we can do the stabilization process in any kind of ambient category of infinity categories where we want to stay. It can be monoidal, exponentially closed, whatever. I don't know, you have to choose the right kind of morphism there. Here we have the adjoints. And just do this thing there. Of course, the thing is you have to know that this colimit exists, or this limit. And it's fact, proved by Lurie, that press L is co-complete.
So if I take the ambient category differently, I could get a different notion of spectra.
Yes.
So you can get like equivariant things or something, or
Yeah, sure. Okay. So that's our category now. It's meant to be such a limit. And I'll just give you a preview of the description of the objects, but I guess I should stop before. So how do I form a limit in usual category theory? I take the product of all the occurring objects then, and then I take a sub-object of compatible families.
Yeah.
Like this would have to be, space x0, space x1, space x2, and so on. And if we are in sets, for example, then I would want that x1 is equal to x0, the compatibility. Well, we are now in infinity categories, so the objects are xi, I and n, in space. And instead of asking for equality, we want the datum of an equivalence here. Let's write it like this, xi plus 1, so xi equivalences. That's part of the datum here. And morphisms are just compatible, are sequences of...
Are we missing some omegas in the description?
Oh, thank you, yes. Omega xi plus 1.
Yes, yeah.
Thank you.
And do we need to state coherence conditions regarding the many FIs?
I think for such a linear diagram, we don't have to, but in general we would have to.
Yeah.
Can you remember me what kind of equivalence we have?
So here we are talking about spaces, so these are just weak equivalence spaces, pointed spaces. Maybe, Should I? Yeah, let's drop this up.
Yeah.
I want to tell you how this was seen more classically. And this was seen through the Brown stability theorem. Saying the following. Yeah, so that's a category of objects like this, and the morphisms would be just the sequences of maps from the xi to y are compatible with all this stuff. So the Brown stability theorem is something that's very classical. Given functor f from the homotopy category, now the really usual naive one actual category sets. It gives a criterion when such a functor is representable in the homotopy category. And here are the conditions, so it should map co-products, which are wedges in top star, products, and it should map push-outs so this should be a homotopy push-out. Since we are classical again for a moment, just let's distinguish these things. Well, this goes to a diagram where the maps are reverted, right? So this B, S upper star, R upper star, C.
Wait, should the maps go the other way? That it's contrary, so.
Yeah, I've done it around twice. That's nonsense. Thank you. B to A, that's I upper star, and here we got J upper star. So for any homotopy pullback that I stick into my functor, this should be a weak pullback. That means I have the pullback property, but just with existence, but not uniqueness. Then there is then this functor is represented. That's the conclusion. So it's naturally isomorphic to something representable in the, or maybe I should rather write like this, in the homotopy category of pointed space.
Excuse me.
Yes.
Is that a pullback or a push out? A weak pullback? Or?
Sorry, pullback. Yes, I wrote it wrong.
Okay.
Weak pullback, but in the same meaning of weak. It's just an existence and not. Yeah, I turned around too many arrows and now I'm confused. So we can check that this holds for Hn for cohomology theory. Yeah, so that's a classical and useful theorem for functors which factor to the homotopy category of pointed spaces. And here's the connection to what we just did. We have a cohomology theory. And each of these individual functors, E star are many functors, right? Satisfies conditions. So this here comes, if you want, from the Meyer-Vitulus property or something. Maybe that's a good exercise. And so we know that En represent we call the space for the nth cohomology function now E lower n. Okay, cool. So cohomology theories is something that I said in the first lecture too, in this hexagon. We had these four properties of cohomology theories. One was homotopy invariance, one was suspension isomorphism. The two other ones were sort of implying this here. Well, one is literally this one, and the other one implies this. And so we know that each individual functor is representable like this. And now we have these suspension isomorphs. So we have, see, for any space X, we have X to En. And let's maybe suspend it, right? Then we get En sigma X. That is En minus 1 of X, and that is
upper index.
Right, thank you.
And also one step before. Yeah, there and there, yeah.
That's right, and now let me see, I have to, boost it up, right? Okay. And this is X to N plus 1.
This is minus 1.
Sorry?
It's minus 1.
Is it? It is, yeah, thank you. Right. Okay, now this here, by adjunction, I can, here I meant the homotopy-theory of what spaces, square brackets.
Yeah.
Sorry, I'm inconsistent. It's not do this. Now I apply my adjunction isomorphism and I have omega here. And since this here, same here of course, is natural in X, by the Unida lemma, I have an equivalence between the representing objects here. And that gives you exactly a spectrum in this sense here. So every cohomology theory is representable by a spectrum, by a sequence of spaces and such weak equivalences between these things. Spectrum meaning object of this Bloch stabilization. Okay, time to stop and think of lunch maybe. That's brought us a bit further through this hexagon, and I think we are in good shape to soon go Motivic. See you.
Thank you. Are there questions right now before lunch? Everybody excited for lunch?
Yeah.
Yeah, okay.